それでは早速、始めたいと思います。アンディ・キーさんです。X86 のメーカーとして、こんなことが面白かったとか、大変だったとかっていう話をしてます。Please.
Thank you. Good evening. My name is Andi Kleen from Intel, Open Source Technology Center. And I've been asked to, originally asked about talking about unique experiences of x86 maintainer. But actually, I'm not sure that the experiences were that unique, so I dropped the unique. So, but I'm talking in general here is just a little bit of introduction. So I hope I won't bore anybody here. So you already know what Linux maintenance is about, I might bore you, but I hope not. And then I'm focusing a little bit on, like when you're working on a project like I did on x86-64 for over 7 years, was maintainer. So how it changes from being small to big. So it's mostly about changes there.
And if you speak slow,
okay, I will try to speak slow. Well, if I have a tendency to speak fast. So if I start getting faster, come on. It's just I sometimes get carried away and then I speak faster, but I will try talking slow. Okay. And just a disclaimer, this maintenance, this happens pretty much all before I joined Intel. So I've been with Intel now for slightly a year now. So it was not an Intel project. And I'm not speaking for Intel here, just wanted to make this clear. So just quick, what is a Linux maintainer at all? So sounds a little bit strange, what is a maintainer? We normally don't have this in our traditional software development, a maintainer. So the main thing maintainer does, of course, is just collect patches. So somebody sends some patches, or the white patches, and then put them in and bundle them together and then pass them up to Linux or to somebody else. Another task that the maintainer does is the release manager, at least for a subsystem. So basically, you don't have to say when it will get released, but you have to at least make sure you do your own code freeze for the subsystem at some point. So you say, at some point, you have to wait for the next release. You cannot put it in this one anymore. You have to keep track how stable it is, how buggy it is, and so on. So release manager work, but typically a separate person in a traditional, again in traditional software development. And then you're kind of an architect. So basically you have to have a kind of a vision. How will the code will look like? Sometimes people disagree on your vision, and other people have other ideas, and so on, or somebody submits a patch which doesn't agree with your vision, and then you have to negotiate or do something about it. So at least you're supposed to have something like this. Then your default blamey, I call it like this. So basically, if something goes wrong with the subsystem, it's your fault. So it's similar to default root, it's just for blame. Yeah? So basically, like if there's a bug or so on, or it makes Linux system not boot anymore, or something like this happens, then you get an email and somebody is complaining. But you also, it's interesting, you're kind of a politician, because sometimes people have different ideas. Like, of course, on a bigger subsystem, like on a small subsystem, you typically don't have this. Like, but if you're working on something with more people working on, many people are interested in, or even companies contributing and so on, you have to sometimes negotiate. So they might have different ideas. You have to have negotiate with them, make sure that you get a single thing in the end, that the thing makes sense and so on. So you have to do a lot of stroking egos, of course, and just talking to people and so on. And the other thing is, I don't know if you, for example, one thing that I was thinking for like a politician is, like, but for a normal politician in politics, it's pretty much required that they have to have an opinion on everything. So if somebody asks a politician, what do you think about this and that? And even if they have never thought about it before, they need to say something. Because if they don't say something, they lose that. And it's the same for the maintainer. So somebody sends, for example, you have a lot of code, and somebody sends you a question or a patch. And you need to, even if you haven't thought about this problem before that the code is addressing, you have to have an opinion. So it's sometimes a little bit of a problem, for example, for me, because at some point you get the idea that you know everything about the subsystem at least, yeah. But for some specific issues, sometimes you need a little bit more study, or the person who submitted it has done a lot of study, and you have the idea you know everything. So sometimes I had to learn at least that sometimes I'm wrong on that one, so I have to reconsider, or I need to listen more to people and so on. That's an experience I had. Yes, so I found it very difficult to have always an opinion on everything. First, I personally found it sometimes hard to just, because sometimes you just don't want to think about things, so you really have to build yourself an opinion on that one. And I must admit, like when I dropped being maintainer, I found it refreshing. I don't have to have an opinion, at least on everything x86 anymore. But I found this a little bit liberating. Okay, another thing is just to basically send the patches for the subsystem to Linux. You collect it using Git. It used to be patches. Now these days it's a Git flow using the Git version control system. So you send it to Linux. Or in some cases there are the sub-maintainers that send it to an upstream maintainer, which collects it and send it over and so on. But you don't have absolute control over the code. So it's not like you own it and you can do whatever you want with it. For example, Linux can override you, can merge a patch directly anytime in principle. They normally don't do that, but it happens occasionally. So, for example, when there's something happens, there are, for example, sometimes patches which change a lot of subsystems. So it's not really that you have just a specific maintainer to merge it, but it's really more a decision, group decision by lots of kernel people to merge it. For example, one example for the x86 subsystem here was somebody designed new timer code, which had a generic timer subsystem, and it touched all the architectures and other code and so on. And in this case, for example, I personally didn't like some things about the timer code, and I delayed it a little bit. So you have some bureaucratic procedures where you can delay stuff, but in the end I was overruled, so you don't have absolute control. And it's sometimes I found it actually hard to not merge patches, because in theory an important task of the maintainer is somebody who can say "niet," as I would say, like a Russian "niet," that's the best word in Russian, you can say no to something. But there are actually ways, for example, when there's for example, Andrew Morton's M3, what Andrew does is basically all the patches who don't find a maintainer, who don't find anybody interested on Linux kernel on the mailing list, which can be quite a lot of stuff, because it's actually some code in the kernel which is just not maintained, or a lot of obscure drivers, for example, don't have a maintainer also, stuff like this. So he collects all these patches, puts it into his MM3, and then sends it to the maintainers. And then they have to say no, or yes, or merge them. But when they say no, they have to explain why no. So you have to basically give a good reason, why is this patch not good, why should not go in. So, and sometimes these patches coming back to you, even if you say no. So sometimes it's hard to not merge something. And of course, every time you not merge something, you typically annoy somebody, because somebody wants it merged. And either it's somebody's features is not going in, or somebody's bug fix, or something else. So that's also interesting negotiation. Okay. You want to thank you. Well, any questions? Yeah. Okay, sure.
一応、カーネルメンテナーっていうのは、基本的にはパッチをたくさん集めているような人で、サブシステムですね。サブシステムごとに、いろんなリリースを出して、コードをフリーズして、その上の、リーナスに提出して、これはサブシステムは OK ですよみたいな話。そうすると、アーキテクトみたいな形をさせていくね。それからやっぱりそういうことなんか問題があるといろいろ 非難をされるんで、ブレーミーって書いてあるんですけれども、いろいろ文句を言われると。それからいろんな人がパッチを入れてくれって言われるんで、ポリティシャンって政治家になって、こっちはいいけど、こっちは悪いとかですね、そんなことやらなくちゃいけない。あとはですね、最終的にヴィーナスにそのサブシステムのパッチを置く。あとはやっぱり、全部イエス、イエスって言ってるだけじゃなくて、このパッチはダメですよと言わなくちゃいけないと。だから、そのためにはなんでダメだったかっていうのをきちんと説明しなくちゃいけない。一番最後のsometimes hard not 回し、回ししてくれって言われて回ししない。きちんと説明しなくちゃいけないというのは大変だと。あんまり回ししないことばっかりやってると、みんな怒っちゃうんで、それとも大変だっていうことで、結構大変な仕事だなっていうのを、なんかすごくあります。
Have you been brained by Lena?
Yeah.
How do you handle it?
Well, you try to address the issue. Or you explain why it is like this, but basically you try to find a solution. Or you back out the patch. That's an alternative. So if say, okay, this patch is bad, then, and for example, it's blocking the release, or so, you just put out the patch and say, okay, we look at it for next release again, or we try to do it differently. But sometimes it's not possible because sometimes the dependencies, so you would need to back out a lot of stuff. So sometimes you just have to fix it somehow. And that means also that, of course, yourself you have to do a lot of bug fixing yourself because you have to look at it and debug it and so on. For example, what sometimes happens to me is I merge a lot of patches and then I put it together and I compile it at the end. And then I tested it on some systems and just didn't boot. So then I have to figure out why it didn't boot. So he has a triple upset, he has a chief debugger.
Quick question.
Yeah.
So how many maintenance does Linux have?
There's a file in the Linux country, it's called maintainers, which has a list of them.
Oh yeah.
But the problem is it's not completely up to date because sometimes these people just disappear and then the person who last changed the code is the de facto maintainer. So people are just looking up in Git who changed it last. But I guess it's 100 plus, as it was just a rough guess. So it's of course there are 4 maintainers. That's already a really small group which are having a lot of code to handle. And then there are lots of maintainers, like there are hundreds or even thousands of drivers. And not every driver actually has a maintainer, but a lot of them have. So that's then people who do very low activity. But I would say it's hundreds, 100 plus. But the core people are maybe 10 plus or 10, 20, something like that. Any other questions?
Do you have some subsystem maintenance, like do you propagate some subsystem code for some other guys to maintain? I mean, your students are maintaining IPv6. David Mira propagates their IPv6 code too.
Yeah, that's a subsystem maintainer.
Do you have?
I had some people who do this way, but I don't have a slide on it. So okay, just a little bit more on maintainer, maintenance in general. On a larger project, so at the beginning, typically, how you start up as a maintainer is you write a lot of code, and at some point you become the maintainer because you know the code best. But when you are on a project which has a lot of users or a lot of code or a lot of impact on the rest of the kernel, then you actually start to spend a lot of time just on administration, so like becoming a kind of manager. So for example, just processing patches from other people, processing bug reports, looking at regressions, doing release management, and so on. So a lot of people who did a lot of coding and they became maintainers, they noticed then they don't have that much time anymore to code. So that can be an unpleasant surprise if you're becoming a maintainer. But of course it depends how big the subsystem is. If you're just maintaining one driver, which is not that often used or so on, then it's not a big issue. But Another thing we have to spend a lot of time on is code review. So in theory, the way it's supposed to work is somebody sends, like, the publication model. Like on Linux, you're supposed to publish your patches on a mailing list, and people are supposed, like, to review them. It's a little bit similar to the scientific process. They publish papers and other people peer review them. The problem is there are not enough code reviewers. So it's sometimes very hard to find code reviewers. So a lot of code review has to be actually done by the maintainers. And typically, even if the code, if patches have been already reviewed, they have to be reviewed by the maintainer again, because the maintainer has to have some kind of quality control. Of course, it depends. Like if there's a lot of code, sometimes they have to do this out, let other people do it, and so on. But typically, maintainers are at least supposed to at least know what's going in. Yeah? So you spend a lot of time on code review, and good code review can take a lot of time. Then, what I mentioned is not that much time to code anymore. And yeah, so especially for complex projects, you have to sub-delegate some things. You just, somebody takes care of that directory or so on. You just pull it in without reviewing everything and questioning everything again, because otherwise you don't have a chance to control the complexity. So kind of, like I say, you become a little bit of a middle manager if you have an important subsystem maintainers. So one thing I sometimes joke is when you're becoming a middle manager is when you're looking less at patches, but only at diff-stat output. At least for these parts. Yeah? For example, Linux is doing most of the stuff just looking at diff-stat. Yeah? And it's okay. I don't think I ever became completely dependent on diff-stat, but sometimes for subsystems. So.
まあ、メンテナーになる人っていうのは、コードをたくさん書いて、いろいろコントリビューションをつけるようになるんですけれども、一度メンテナーになってしまいますと、コードを書く時間よりは、一番上にあります、アドミ、要するに、そういった事務処理みたいな仕事が増えてきてしまって、あんまりコードを書く時間がなくて、本当にそういった事務的なこととか、レビューをしたりとか、特にまあ、彼も言ってましたけども、今、本当にすごいたくさんの人がコードをカーネルに開発でコードをたくさん入れてるんですけれども、レビューしてくれる人がちょっと足りないんですね。で、結局、メンテナーの人たちが、最終的にコードをレビューすることになってしまうので、書くというよりはレビューして、それをどういうふうにいいものがあるかっていうのを確かめてあげるということが多くなって、一番最後に言いますけれども、中間管理者というふうに、まさに言いますと、実際にコード書いてる人も中間管理者という感じでしまうのかなというところです。なんかある意味で、こんな感じです。
メンテナーズファイルによると、537人の名前がありました。
Maintenance file includes 537 people.
Okay.
Yeah.
537.
537.
Okay, that was a bit low, but a lot of them are inactive.
Yeah.
So more better thing you can look at git logs. If you look at the people who do sign-offs, so that there are some statistics. I think Linux Foundation has a paper on that. I think, but it's always difficult. There are lots of people trying to estimate the contributors, but the really core people, that's a relatively small group, I would say. Okay, code review a little bit. In general, good code review is hard work because you have to understand it, you have to follow up and check everything and go through the logic, and it depends. Like they're different, of course. In some cases, if somebody is changing a core piece of your subsystem, you check a little bit much more closely at it. And if somebody is just changing an optional module, which is sometimes compiled or not. And also, for example, for code review, the more you're going towards release, the more code review you have to do, because you have to make sure that that it doesn't break the release, this patch. And it's also it also of course depends how much code review you do, how much you trust the contributor. So if you have somebody who has done a lot of good work in the past, you don't look at their patches as closely as if somebody was new. You have no idea if they're good or not. And the code review is pretty important to keep Linux coding standards up. There are lots of things which are known by experience, by long-term developers, so you have to double check this. Now, like for example, now recently there's something called check patch PL, which checks some things, but there's still a lot of other things which you basically need a human to check. And normally, of course, the ideal way is you have to have the patches posted to mailing list, Linux kernel or not mailing list, and then people who are there just read the patches and comment on them. So even if they don't have that much experience, still people who has any basic C code ability can typically look at the code, and even if they don't understand the complete kernel, can say, hey, this looks fishy, something must be wrong with that, or things like this. So that's normally what we would like to have to do, but again, unfortunately, code reviewing is not so sexy. So not many people do it, yeah? So it's difficult to find code reviewers. So again, the maintainer has to often do it. And code review, that's often an iterative process. So you tell them something, you have to change that and that and that. And then it comes again. In some cases, it iterates multiple times. Sometimes can even go on for weeks and longer in complex cases, especially when you have to iterate on a design. If you say, okay, your design has a problem, you need to change the design, then it can take a long time. And it takes a lot of time of the maintainer. And just one thing in general, if you want to contribute to Linux kernel, just doing some code review is definitely appreciated, even if you're not an expert in particular, but just if you can understand some code and just look at it and say, and even if you just ask a question, that's pretty good. I think it would be a pretty good contribution if anybody is interested.
まあ、コードレビューは大変だから手伝ってくれっていうのが最後のメッセージなんですけども、まあ、といっても、まあそうですね、だからコードレビューは大変だということと、それから、まあ、自動的な実用でもさっきちょっと言ってましたけども、あるのはあるんですけども、やっぱり人間が確かめなくちゃいけない、人間が見て確かめなくちゃいけない。で、まあ、でも、ある程度、なんかいいコードをしてくれるに対しては、そんなにチェックしないで済むというのがあったりします。あとは最後にちょっといいポイントがあったんですけども、コードレビューって、エキスパートの人がこうするんですしなくちゃいけないということはなくてですね、例えば、なんか質問してあげると、このコードってどうなってるんですかっていう、そういう質問も、まあ、レビューとしてはいいんじゃないかなという、まあ、そうするとですね、多分、書いた人も説明しなくちゃいけないんで、もしかしたら間違いに気がついちゃったりするのかなという感じなんです。まあ、そういったところで、ぜひ、そういったところでも、貢献をしていただけると助かります。
How many code review process do you have at a time?
You mean in parallel?
In parallel, usually.
Oh, multiple ones usually. It depends, like there tend to be long-running ones, which go on for weeks, and then short ones. So at least a few, typically. I had at this point when I was maintaining this. In the worst case, maybe 10 or so. Something. At some point, you have to stop it because you lose track of the complexity. But it was not typically a larger number. Any other questions? So a little bit on, finally on x86 maintenance. Originally, I started only working on the 64-bit part. That's where I originally started. Was a project done by SUSE starting in 2000. And originally, when it was started, there was no clear maintainer. There was just a couple of engineers at SUSE who basically did the kernel work. Like I did some parts, but other people also contributed a lot, so I did not do it on my own. Of course not. But especially once you go public with the project, you need a maintainer who is the interface to the world. So like, for example, sends patches upstream, or keeps track of the releases and so on, things like this. So at some point a maintainer was needed. And for some reason, I still not completely understand why I ended up with the job. But probably some other people could also done it. So back then we had an x86 kernel maintainer. It was actually before it was merged to mainline. So the project existed for quite some time before it was merged to mainline. But of course, also the project has also GCC maintainers, and glibc maintainers, and GDB maintainers, and there's other people for all these components that you needed to have a port running. And they also did great work, of course, the other maintainers, and of course, also the other contributors. So, after it got to the mainline, so a long time I was only focusing on x86-64, but the one issue was that x86 actually didn't have a dedicated maintainer. It was just done by multiple people or the Linux. It didn't have enough time. So at some point, because it was doing a lot of stuff for 64-bit, as it became the de facto x86 maintainer too. But never put it in the maintainers file because I never wanted people to think of me as it, but I had to basically also review the patches and so on.
When did you start originally? When was 2000?
It was in 2000.
ですね、もともと x86-64 のメンテナーだけだったんですね。まあ、補足説明していただくと、x86-64 というのは最初 AMD があったんです。そのプロセス。
And that was a simulator back then. We only worked, because there was no hardware, we only had a simulator, so that was not really hardware.
まあ、ハードに関係なく x86-64 の、60ビットの、ワークをしてたと。で最初は数勢の中で何人かでやってきた、まあ中で何人かのグループでやってたやつなんですけども、それがいろいろ、x86-64 のハードウェアが出てきたりとかして、まあ、いろいろ注目されて、まあ、いろんな人たちとインタラクションしなくちゃいけないので、まあ、そういった意味で、まあ、正式というか変ですけども、x86-64 のカーネルメンテナーになっている。で、カーネルメンテナーだけじゃなくて GCC とか glibc とか GDB とかのメンテナーもやっていると。で、もともと x86、まあ、i386 って言ってますけども、x86 っていうのはサブシステムメンテナーってなかったんですね。普通 CPU ごとに ARM とか SS とかあって、あとは、ファイルシステム、サブシステムのメンテナーっているんですけども、まあ、i386 ってデファクトなんで、まあ、そういったメンテナーいなかった。で、結局彼がですね、x86-64 をやってたことから、まあ、ここにあります、デファクトの i386 のメンテナーになってしまったと。ね、
Thank you. Okay, just probably most, I assume a lot of people know this already, but I'm just repeating it here very quickly. So just in the old model, like originally they had this 2.4, which was kind of the stable kernel, and then 2.5, the development kernel, which became then 2.6 at some point. And originally when the port started, there was in 2.4 only, and then actually after the port had started, it had forked from 386 to 5, 2.5 tree was forked. So I had to maintain at least 2 trees. I had a 2.4 version and a 2.5 version. And the problem is 2.5, there were lots of changes there, so it became quickly quite different from 2.4. It was a quite different tree. And later on, we had also done distribution trees with backports. So for example, the tools that were shipping /8, which had kind of forked, and a lot of changes had to be backported there. So at least 3 trees to manage. That was the old model. At some point, the new model, which is now in action for several years and works very well, is because everybody realized that this long disconnect between stable and unstable doesn't work very well. Now we have this 3-month cycle, basically. So you have 2.6.x and then 3 months 2.6.x plus 1. And the 2.6.x is a stable tree, and then you have the next one. So you don't have this gigantic disconnect. But So right now you kind of have only two keys to manage, and they're not too different. So you can typically just move the patches between. But also especially when you're working for distribution, like I did, you have to also care about the distribution tree. They have a stable tree, the last release, maybe even multiple releases. Like in the SUSE case, they have the enterprise release and the consumer release, even multiple ones, and so on. But that's the new model.
これは皆さんご存知かとは思うんですけども、オールドモデルです。
No, I think earlier than that, 2005.
この上の方のオールドモデルっていうのは2005年ぐらいまでだったと思うんですけども、カーネル 2.4 と 2.5 って両方並行で開発を進めていって、まあ、プロダクションバージョンみたいなやつと開発バージョンで2つ進めていって、やるっていう、まあ、方法を取ってたんですけども、その後ですね、この2つあると2つともサブシステムでは適用なくちゃいけなくなっちゃうんですけれども、まあ、それやり方をちょっと変えようということで、2005年から6年ぐらいからですね、新しいやり方に変わってきてですね、こういう2つのツリーじゃなくて1つのツボになっていく。毎3ヶ月ごとに、1回新しいカーネルを出していくと。で、その、まあ、ちょっと補足になっちゃうんですけども、最初の1週間か2週間っていう、マージウィンドウって言いまして、そこでXがいざ復帰して、後でその3ヶ月の残りの週間で、コードをきれいに固めていく、バグとかを取るんですね。で、3ヶ月後に新しいカーネルパッチをリリースという、3マンスサイクルっていうのを、最近やっています。
So, just what I said earlier, focusing on the changes. So one thing is, especially what I found is very different. At the beginning it was a novelty, especially when we were in the simulator only phase. We were only simulators, there was no hardware. So people only said, oh, somebody did 64 x86, interesting. So then later on, when hardware started actually shipping, and we had real users in the field and so on, then it became more widely used, and people were actually relying on it. And then over time, when pretty much nearly all x86 now supported, okay, nearly all, so like, it became more and more commodity. And I found it a big change, because for novelty, you can basically do whatever you want. Of course, you have to do the project going, but you don't have too many external influences and so on. And if you move towards commodity, then everything gets much different. You have lots of stakeholders, and you're impacting a lot of people, and you have generally much more complexity. So the complexity in general, when you go to commodity, is rising significantly. Not as much necessarily in the code. The x86 code is actually something, I think I've been growing a lot recently, but the beginning was something like 30,000 lines in this ballpark. But just the complexity of all the interactions with platforms, different biases, different systems and so on, and different users, that's growing a lot. So you have to manage a lot of things. And the release management gets a lot more complicated. So what I found difficult was interaction with other subsystems. So for example, API or specific drivers or changes which impacting all the architectures, or for example, the example I had earlier with timer subsystem, or lots of other things which, for example, you have to crash dumping, then they also have to impact you and so on. So you have to spend a lot of time just negotiating with other maintainers. That's the politician part I mentioned earlier. So that all becomes much larger to go towards commodity. At the beginning, it's not so big an issue. But we also did later at the beginning, pretty much I did a lot of code, my colleagues did a lot of code. We had a few contributors over time. But later out, we had to farm out a lot more work. For example, at the beginning, ACPI was also extremely exotic, and people normally didn't enable it. But over time, ACPI became a lot more important, and we actually found out a lot of issues we were having the ACPI people, because there are lots of, basically ACPI has a lot of interaction with BIOSes, and we have a lot of problems in this area because there's so many different BIOSes and so many different BIOS bugs. So it probably would have not been manageable. Had needed to done everything ACPI too. So fortunately we had very capable ACPI people like Dan Brown now, a colleague at Intel, and his team were doing extremely good work. So that helped a lot. Oh, what's happening? Sorry.
上にノベルティっていうコミュニティって言ったんですけど、もともと x86 がハードウェアがなかった時代からやってて、どんどんそれがハードウェアがどんどん広がっていったんですけども、最初はやってる人でも少なかったし、そんなになんか注目されなかったんで、注目されなかったって変ですけども、自分たちは好きなことができたんですけども、やっぱりそれがハードウェアが広がってくると、そのコミュニティになってくると、いろんなところから、影響が及ばされてきて、自由にできなくなってきてしまったと。で、特にですね、自由にならないし大変なことも多いし、コードもたくさん多いんですけれども、やっぱりプラットフォーム、いろんなプラットフォーマーに、採用されているんで、そういったところの問題にもいろいろ書かなくちゃいけない。あとはやっぱり、それがメインになってくるんで、いろんな他のサブシステムとか、タイマーとかいろいろ言ってましたけども、そういったところの人たちと一緒に、インタラクションというか、いろいろやり取りしなくちゃなって、そういうのが増えてきてしまって、またさらにさっき、ちょっと管理職ってありましたけれども、そういった色が濃くなってきたと。で、ちょっと ACPI のところ、私もよく分からなかったんですけども、ACPI って結構いろいろ問題があるみたいで、
ACPI の BIOS 自体にいろんなバグがあって、一つのなんかサブシステムで動いたからといって、他のサブシステムに持っていくと動かない、他の会社のマシンで動かすと動かないとか、同じ会社のマシンでも次の世代でやると動かないとかって、そういうことがすごくよくあって、非常に大変なメンテナンスをされていると思います。
多分これは ACPI ってスペックあるんですけども、若干緩いところがあってですね、そのバイオスメーカーさんによっていろいろインプリメンテーションが違ったりして、多分そういったところですね。そういったところで苦労されている。ということで、プラットフォームがすごいたくさんあって、ここにかける力というのが、たくさん出てきてしまいましたという話がありました。
How do you handle the bug that you cannot reproduce your platform?
You have to work with the contributor. Sometimes, for example, one thing we did was we had contacts with some vendors. So, for example, there was, for example, an NVIDIA problem, and we had at later point we had contact with NVIDIA and asked them to look at it. But in some cases, we have just worked with them. And the problem is, especially for at least cheap consumer parts that are done somewhere in Taiwan, there's nobody to find who cares about it there. So in this case, you just have to work with somebody. But that also is extremely time consuming because you have to interact and ask them to test something and so on.
So you said BIOS issues. I think there are some 2 or 3 BIOS vendors. What do you think is the best BIOS vendor?
But the problem is not so much the way it works basically. There are lots of people who are contributing to your BIOS. So first you have the BIOS vendor like AMI or Phoenix and so on. But then there's some code that's coming from the CPU vendor. They have CPU code in the BIOS. Then you have some code for the chipset that initializes the chipset. And you have some other code. And then the company who does the motherboard or the platform also adds some more code for specific features. And every time they do this, they can add interesting new problems. So lots of possibility to break things. And especially, okay, later, but one issue there was if it's not used by Windows, it doesn't necessarily work because they don't test it and so on. That's one issue there. So.
バイオスメンがどこがいいかっていうと、そんな単純なことだけで、バイオスもやっぱりハードウェアに合わせていろいろ作 くるんで、そういったところもあるんで、一概には言えないと。
Okay, just more on the changes to the project. I personally found them very interesting, or changed over time. So as I said earlier, the first implementation was just a simulator. And we actually had two simulators. We had first a very slow simulator, and then later on a faster simulator, because the slow simulator was really too slow. And at some point, we basically had it working on the simulator. But actually it didn't take that long, maybe something 3/4 of a year or so. Then it was pretty good on the simulator. And also X worked, and some compiler was pretty good, and so on. And then we had the problem, we didn't have hardware. The hardware was late. And we actually were faster than expected. So we spent a lot of time just waiting to actually get hardware, because you basically limited what you can do in the simulator. Simulator are pretty slow. You can't really use them every day. So some testing can be done, but not complete testing. And so then I spent a lot of time just waiting, forward porting it to the ACTO and 2.5, forward porting to the 4, and stuff like this. So I was joking, especially for 2.5 at this point. I was probably the only user in the world who ran 2.5 on x86-64 at this point, because nobody really else testing it. And of course, I couldn't test everything myself, so there was some bug testing. And it was pretty long. I think it was over 1.5 years. Like I remember, I was going to conferences and joking, yeah, I'm the maintainer of a simulator architecture. So then the next thing that came was we had a single hardware platform. So it was a single box basically, and we of course we booted up. Actually, it worked pretty quickly, but we still of course found a lot of bugs for stuff we couldn't test on the simulators, or that cause it run faster on the hardware, or you could test a lot more things. So for example, you couldn't run KDE, for example, on the simulator, because it was not really usable. So we found a lot of issues there. But actually it was not too bad when we did this. And it was actually pretty easy to get a single platform running completely. So you can just look at everything and fix it and so on. That was the single platform stage. That was the next stage of the project. Then after some point the platforms keep growing. So there was another one and another one. But still only from a single vendor. So it was still relatively controllable, because you could complain to the vendor and they would actually fix the BIOS if something was wrong and so on. But still isn't pleasant, not too problematic. Then at some point it became mass market. It was a lot more interesting, lots more vendors doing different BIOSes with different issues. Then new chipsets came in, which had lots of interesting new issues. Then at some point new CPUs came in, so it became bigger and bigger and bigger. That was the next stage. And today, of course, it's nearly everywhere. So actually there's a little bit of a drawback, because most of the netbooks don't have 64-bit support. The CPU actually supports it, but it's not enabled for some marketing reason. But still, most of the PCs bought today, they have 64-bit. So, and of course the complexity is gigantic, because there are so many platforms. Nobody even knows all the platforms. So, and I found it a lot. The changes were very interesting here. So especially complexity was on. Basically, I had to move more and more into the manager and politician role as we're going towards the later stage, because you have to interact with much more people and much interesting conversations and so on, and farm out a lot of work to other people.
I think the simulator is software.
Sorry?
Simulator is software.
Yeah.
How slow is it compared to hardware?
It depends. We first had a simulator which was really extremely slow. So it took something like 15-20 minutes just to boot. And we had actually, what we did is, because it took so long to run to the BIOS, simulate the BIOS, we added a special hack to dump a new memory image into the save. You could save an image to this, and we had a special hack that the uncompressed kernel was put into the image, just we didn't have to wait for the BIOS all the time. But later on, we got a new simulator. It's a commercial one. It was called Virtutek Simix, which is still maybe factor 20, 30, 50 slower than a real box. But at least you can type something in. You can start VI, and it actually reacts to your key presses in reasonable time. So that was, you still couldn't do a lot of stress testing, but it was much more faster.
これはまあ x86-64 のメンテナーっていうか、開発やってた人たちの、最初はシミュレーターでやってた、ハードウェアないんで、ソフトウェアで CPU を x86-64 のシミュレーションするやつで、そこで開発をしてた。でどれぐらい遅いんですか、性能遅いんですかって言ったら、ブートするまで20分ですね。ブートするまで20分ぐらいかかるぐらいの遅さですと。それも後半は良くなってきて、そのシミュレーター上で VI を使ったりとかするのができるようになったらしいんですけども、そういうソフトウェア上のシミュレーターで、最初、それを開発をして1年以上待ってやっとハードウェアが1個出てきて、それを大事に使っていって、それが少しずつ広がっていって、今では、ネットブックでは64ビットないんですけれども、ほぼ全てのパソコンに、64ビットが使われていて、Everywhere in PC スペースということになっています。それに伴って、もう一回ですけれども、先ほどと同じように、いろんな方との、インタラクションというか、総合的なやり取りが増えてきてしまって、そういったそのポリティックな動きとかですね、そういったマネジメント的な、アドミニス的な、仕事が多くなっています。というところですね。
Okay, I see I'm pretty far in the time already. Is that a problem? Or?
It's okay, but we are waiting pizza, so until then,
okay.
you can spend any time.
Okay, I didn't factor in the translation. I'm sorry. That's why I normally expect it to go a little faster. So I might cut up some stuff today, but I don't have that much things anymore. So just very quick how it got started. So basically we just copied over Arch386 back then and removed a lot of code because there were a lot of old hardware workarounds and bugs and strange code for old systems we didn't care about anymore. So it was really nice to get rid of a lot of crappy code. I still remember this one. It was an extremely interesting coding session. The goal was to get a much cleaner board basically. For example, it runs everything only on a modern PC. Modern PC is in many ways different from older PCs. So try to be basically get rid of old bugs. Then of course implemented 64-bit. It was done by a team, and we redesigned various code areas. So for example, stuff like Jesus call or completely new interrupt entry code, or various other areas like interrupt stacks and some other things. A lot of other things were redesigned and developed and so on and tuned for the current platform. Then, as I said earlier, there was a long hiatus for over a year because it was basically done on a simulator, worked on a simulator, but there was no hardware yet. So most of the team was going to do other things again. So I stayed and did 2.4. It didn't change too much, but I had 2.4, 2.5, and I was probably the only user 2.5 at this point. And I found it very tough if you don't have too many people there, but it was interesting.
So how many people do you have in that team?
Originally, at the beginning, we had something like, let's say 5 or 6.
5 or 6 in SUSE?
Yeah, in SUSE.
Okay.
And then I think over time fluctuated, but then especially in this long simulator time, it got cut down a lot because there wasn't really much to do for other people. So you just need a maintainer and other people occasionally doing work. There was basically at this point, for kernel side, there was only me for some time. And then later on, of course, more people again.
Why was SUSE so eager about supporting x86-64?
That was interesting for the future, like interesting project. We are also working with other companies who are also interested in it. So there were some business negotiations and so on. And so SUSE was interested in it going for the future. So Especially one thing that for SUSE is like SUSE typically had they had some kernel engineers who were contributing to code, but had never really done so really big projects in the kernel before. That was one of the first projects I would say at SUSE. It was done by a larger group of people in the kernel. So I think at least my impression was that it raised the profile of SUSE a lot. So it was pretty successful for SUSE. Like a lot of companies didn't want to talk to SUSE before. After the project they did. So it was.
これはx86-64を開発していく中でどういうふうにやっていたか具体的なところですよね。最初にその386のアーキテクチャのところから、昔のハードウェアにあったような古いコードをちょっと捨ててって書いてありますけども、そういったところゲットリードって書いてあるんですけど、そういったところを捨てていってまずクリーンアップして、それから、64ビットのところを、サポートをインプリメントしていったと。で、そうですね、ちょっと例えばその 2.5 は大変だったとかってあるんですけども、大体5、6人、もうちょっと5、6人で、1人でやってた。で、全部スーゼの社員になってで、なぜやってたかっていうと、スーゼとしては、将来の、コンピューティングというのは64ビットだと。で、そのスーゼからそういったキーのメンテナーを出していきたいという会社の方針があって、彼も含めて、このプロジェクトに、モチベーションすることができた。
Thank you. Some headaches we had, some problems. I already mentioned most of these, especially when we had a lot of mass market works going up and there were suddenly 5 chipsets instead of 1. And most chipsets, they have some quirks. Some vendors are worse than others, but usually some issues you have to address. And controlling these all was tough, especially from the smaller vendors which don't give you any documentation. So I think sometimes they don't even have documentation on bugs and so on. So it was quite interesting.
How do you get documentations?
Well, it depends. Like larger vendors like Intel, for example, publish documentation publicly, so that works pretty well. Smaller vendors, well, typically you don't have documentation. Sometimes you can talk to them and they give you something, but sometimes it's not really useful. And for other vendors, you don't get anything at all. So you have to just get through somehow. BIOS, I already touched this before. That's an interesting challenge. So especially now it's getting a little bit better, but it used to be that if you use something in the BIOS or in ACPI which Windows didn't use, then it just didn't work in many cases. So for example, one thing in the ACPI code, ACPI is a code where the BIOS provides some code which is run by the kernel, and the code can ask the kernel what operating system it's running on. And originally it said, I'm running on Linux. But the problem was, when you say running on Linux, they even have this code path in the AML code, but it has never been tested. So if you say you're running on Linux, you're basically running untested code, and that often doesn't work well for obvious reasons. So actually at some point Linux switched over to say I'm Windows XP, because that worked a lot better. But in general for BIOSes, servers are better than clients because they basically have more money, more engineers to spend on this, and they are also more interested in running Linux. Okay, this has changed now a little bit, but it was back then at the beginning of 2000, there was typically not much interest running Linux on the clients. Also in general, the cheaper the system, the worse the BIOS, because obviously they don't have as much time to work on it, and they do it very quickly, and they don't support it anymore after it comes out. Not much bug fixing. But not even the expensive system have occasionally very interesting bugs. So we basically had to do a lot of BIOS workarounds. And it's difficult because you always have to make sure that you don't break something else. So there were lots of interesting negotiations and trade-offs going on here, just working around this. It's basically like an analogy is, it's not like, for example, if you're writing just code normally, you're talking to some other subsystem, you have a spec, you know it works. But here, it's more like you're talking to lots of other people, which in theory is supposed to follow a spec, but they don't completely. So it's more like navigating a foreign country. and you don't know in advance everything about this company. So you just have to throw out the code, and some users run it. That's very difficult. And of course, luckily, a significant part of that later was handled by the ACPI team. At the beginning, we did a lot of it ourselves, but still, we had a lot of non-ACPI bias issues.
Sometimes it is pretty difficult to get documentation of BIOS, right? And there is no specification behavior of some specific functionality. And you cannot decide whether it is bug or functionality.
That's correct.
Yeah. How do you decide whether it is bug or
It's
functionality?
very hard
Yeah.
to do this. So you do a lot of trade-offs and guessing and so on. And trying, especially when you're going towards release and you have to do some workaround, you have to be extremely sure that you don't write something else. So that's always very tough to figure this out.
ちょっと難しかったけどですね、まあそういう言ったら蓄積とかもたくさん出てくるんで、これも大変だと、特にまあ別にバイオスも蓄積ともそうなんですけども、まあはっきりハードベンダーさんが、十分にデータシートとか出してくれない場合が、まあインテルとかはオンラインでデータシート載ってますけれども、まあ多分台湾の結果とかって怒られるかもしれないけども、そういうところは結構ですね、ドキュメントがなかったんですね。でそういったところは結構大変だったというと、あとはやっぱりバイオスメガさんも Windows 結構いい加減に作ってるのかどうかわからないですけど、Windows で動くと。でも Linux で動かない場合が出てきてしまう。これはもうメーカーさんの方はすごいよく知ってるのかもしれないですけども、そういったことがありましたとかですね。ですね、まあ、バイオスのワークアラウンドといって、まあ、バグを直すためにいろんな仕掛けをしなくちゃいけないんですけど、そういったところがたくさん出てきますとかですね、あと ACPI の、チームの人たちと、まあ、たくさん一緒にやらなくちゃいけなかったことがありますので、そういったところをなんです苦労話なんですよ。When do you think EFI become more real?
Well, actually, like for input systems, EFI is very widely used, but it's very well hidden. So there are more systems for using what's called Tiano. That's an open source project which is EFI bus, but they typically hide it and it doesn't look like EFI. So it's actually getting out more, but the actual EFI interfaces are not getting used too much. There's not much on that, but the EFI code base, or internally there's a lot of EFI, more and more EFI. Okay, doing this very quickly. I already talked most of this, but basically, x86 didn't have a dedicated maintainer, which actually resulted in my opinion, code being merged. I didn't like. For example, there was a very strange implementation of sub-architectures and some other issues. So when I was doing more and more work on 64-bit, when it was mainstream, I had a lot of the issues that was fixed on 64-bit had to be fixed on 32-bit too. So actually, I did a lot of changes in 32-bit too, and I became kind of the de facto maintainer of 32-bit. So kind of decide my the original plan at some point we had then was basically because at least in my opinion the 64-bit code base was cleaner and didn't have many strange things, and 32-bit one had. So at some point we had a plan to add, it was actually a suggestion from Windows, to add 32-bit support to the 64-bit code base and use the old 32-bit port only for old systems. That was one of the plans. But basically would have gotten a cleaner code base, kind of merged more code and so on. But it never happened due to time constraints. So, of course now there's a different effort going on to merging them that is has different ideas. So that was the original plan that would never happen.
これさっきのちょっとまとめたような感じですね。もともと386っていうのはメンテナーいなかったんですけれども、386の、最終的には386のメンテナーを入れることになってしまったけれども、フォーカスはあくまでも64ビットです。そこに30ビットサポートを加えていますといったことですね。
386のメンテナーってイゴモナとかアラフォックスとかアンディドキュメンテッドなグループの人でメンテナーされていて、でだから自然とこう60ビットやったらアンディも32ビットのメンテナーに自動的に組み込まれてしまったという。
Next one. That's one area. Okay, I worked on a lot of areas, but one area I found interesting was the compat layer, because one of the big
headache. Headache.
You had it?
Yeah, nothing. Compat layer.
Anyways, one of the big advantages, of course, of x86-64 compared to some other high-techers is that you could still run the x86 software at full speed. So it runs still at full speed. It's a perfectly good 32-bit system. But we had, of course, translate the 32-bit system call to 64-bit. So we had to write a compat layer at the kernel level. Of course, typically when you're talking to purists, you say, well, all free software can be recompiled and then should just work, so why do you need a compat layer? But it turns out, even for software you have source code for, a lot of at least at this time point, a lot of code was actually not 64-bit clean. So they had problems running 64-bit systems or with duplicating pointers and stuff like this. So it didn't work when you recompiled at 64-bit. As I personally find it very useful to just use all binaries and not recompile them. And of course, people who are running binary-only software, they don't have any other choice. So a compat layer is useful. So the way we started is, we did actually, because there were other operating systems, like for example Spark 64, the way they operated is they did everything through the compat layer, because they have a 64-bit kernel, but they did nearly all the user land was 32-bit only. So every time you run a Spark 64 system, you can run everything through the compat layer. That's also today true for some other architectures like PowerPC. They typically have only 32-bit user land, even if you have a 60-bit kernel. Basically, we took the code, we had to do a lot of changes, but that's how the current code was started. Of course, originally we had some second thoughts, like we said, okay, maybe it could be auto-generated somehow. So you could describe a language, and then just auto-generate the code with a mini compiler or so. But because there was already this big code, we could just take. We decided not to do this, and long term that might have been a mistake. We might have been more happy today if we had it auto-generated, but that's how it happened. We just took it and copied it and worked on it. And I would say my estimation is it's 98+% compatible. So you can really run a lot of things. So probably even more than that. There are only a few things like you directly access proc. There's some issues on, but you can. What I did for a lot of testing, for example, I was just running 64-bit kernel and then putting a standard 32-bit up distribution on the 64-bit kernel, and basically everything worked. It was pretty interesting. Another thing we did, for example, was to implement AOut support, which was the first for a compat layer. And it was pretty funny back then, because back then the last SUSE release, which was AOut based, was already, I think, over 5 years old or something like this. And I asked around, does anybody still have an AOut SUSE I can test my compat layer on? Because it was pretty hard to find any AOut binaries anymore. And they actually said somebody still had a backup tape, but restored the backup tape, and nearly everything worked. I think the only thing that didn't work, but it wasn't the fault of the compat layer directly, was Emacs, because the problem was that it had a larger address space. And this really old Emacs version didn't like a larger address space, because running combat mode, you have a 4 GB address space instead of typical 3 GB address space. So that was the only thing I found that didn't work. Only could run the A out and C root. And another thing was really interesting experience was Wine. Because Wine is 32-bit, but also runs 16-bit code, like old Windows 3.1, 16-bit code. I still remember this, for example, I was visiting at the SUSE office at this point, and I was working on this, and I got Solitaire to work after had to do some changes to the kernel, and I said, oh, cool, I got Solitaire to work. And I was sitting in an office with another guy and said, oh, what he's saying. He said, oh, I got Solitaire to work. It was a really interesting situation. But the funny thing is, what I like to point out is, when Microsoft did 64-bit Windows, they actually dropped 16-bit Windows support. They don't have a compat layer with 16-bit. But on Windows and on Linux with Wine, 16-bit still works. So we're actually more compatible. And I learned a lot about corner cases, especially later when I got bug reports. Some vendors are doing really interesting things in their binaries, and was very interesting things.
最後のは面白かったんですけど、私の方が忘れちゃったんですけど、基本的に、まあ、コンパクトレイヤーっていうのは32ビットのカーネル環境下で64ビットの環境下で32ビットの、コードを動かすためのレイヤーなんです。まあ、別にそのなくてもコンパイルしなせばいいんじゃないということもありますけれども、まあ、バイナリーがそのまま32ビットのバイナリーが64ビットの環境下で動くことが大事だと。便利だし、ということでこれを作ってます。まあ、ご存知かと思いますけど、32ビットと54ビットだとポインターとか違っちゃうんで、そこら辺の問題があるんですけれども、そういったところをやって、最後にですね、ちょっと時間も時間なんで、ワインですね。ワインっていうのは Linux 上で Windows の環境を提供するものなんですけども、きちんとWindows の場合は32ビットの前に16ビットの環境も、あってですね、そこの、きちんと考慮にしなくちゃいけない。で、彼はきちんと16ビットのところまで考慮に入れて、昔のDOSのとかのですね、アプリケーションですね、これを動くようにしたと。ところが、Windows の64ビットバージョンもですね、思いっきりその16ビットのサポートをやめてしまったということで、Windows よりも Linux の Y の方が昔の、DOS のアプリケーションを動かすことができて、コンパチビリティが高いということで、最後の話を終わりました。
その前のレイアウトの話も面白かったんですけど、レイアウトなんて今更サポートしなくてもいいと思うんだけど、そこまでやったらレイアウトがだってカーネル 2.0 になった時だし、だって ELF サポートするようになってからもうレイアウトサポートしなくなったんで、だからあれ1998年とかそれぐらいからもう使ってなかったんだけど、そんな古いバイナリーも
でもあんまりコスト高くなかったよね。
まあそうかもしれないですけど、わざわざ店舗からそんなバイナリー持ってきて頑張ることじゃない。それは趣味なんですけど。
Okay, a little bit more on compat layer. Really, I would say the current compat layer was a success, like very compatible and really good. But still, in practice, one lesson I learned is that's not good enough if you just have a good kernel. You also need good user land. The issue is basically, if you still run the binaries, because they're linked to shared libraries, and if you want to run 32-bit binaries, you have to have 32-bit shared libraries too. And back then, the way it was originally designed from our team was lib64, where you put in all the 64-bit libraries in lib64, and the 32-bit libraries stay in lib. And that was implemented by a couple of distributions. But the problem is some distributions just didn't follow. They never did this change over. They never really shipped 32-bit binaries. And the problem is basically the compat layer doesn't work with 32-bit binaries. So that's why, but I consider at least a failure. I didn't do enough education there. I should have educated people more that you actually need this. So the problem, right, in my opinion today, one big issue with adoption of 64-bit is there's some popular distributions. I don't want to name names or blame anybody, but it's just saying they're out there. They don't ship it, and for them you can't run the binaries, and that's a large problem with adoption of 64-bit today. in my opinion.
カーネルレベルでは、コンパクトレイヤーといいんですけれども、ちょっと単純に見たアプリケーションをやるためには、ライブラリーが必要になってくると。でもいくつか、ライブラリーを、でない、ディスクションがあって、困ると、どっかは言わないですけどって言ってましたけれども、それは後ほどビルの中から聞いてください。
Okay, another thing I already touched it earlier is bug management, especially when you're going from novelty to the commodity phase. So I still remember, because in the early phase, like we had only a single platform or a recursive platform, basically I could keep track of all the current bugs. And I still remember the day, I can't tell you the date, but I remember it, then I realized it, I couldn't keep track of all bugs anymore. It was a pretty sobering experience, because kind of you develop a little bit of a control freak stuff, and then you have to say, okay, I just can't handle it anymore. Some things have to be handled by other people. And it was pretty interesting, and I thought it was a big change for me at least. Originally, what I did always, I had regular releases, like it was a patch kit, and I had just a bug list in a text file that keep track of things. Then later, of course, with some other stuff was handled by other people, it was difficult to track regressions in general for releases and to determine release readiness. So when it's actually, when do you have the code freeze, and can you actually say, okay, it's good for release. Later on, some bugs got handled in Bugzilla, kernel.org, and also some bugs got handled in distribution Bugzilla. But at least a lot of kernel subsystems still do it informally. So the main exception for the main Linux maintainers is ACPI, because they have so many bugs, they need every help they can get. It's not saying that the ACPI subsystem is so bad, it's just that there's so many BIOS issues which they have to track. I don't think I ever got a perfect grip on the bug management there. So sometimes was a little bit informally, but typically it worked, and we got a lot of releases out. Probably could have done it better. But one thing that came out later, people were actually doing central bug mastering. For example, there's one person now, Rafael Visocki, who has a regression list, which is extremely useful. In general, people, what they found out was extremely important job in development is somebody called a bug master. Bug master is, because a lot of bug reports turn out to actually not be very useful. You have to ask them a lot of questions and supply the information, and the bug master just makes sure you actually have a useful bug report and then categorizes it. And that's extremely helpful for the maintainer. So, and still I think it's one of the big issues with Linux today is bug management is important. So again, on the team earlier, so if you're interested in doing something on the kernel, bug mastering, so just looking through Bugzilla bugs and so on, is maybe not as cool as sending a patch, but it's extremely useful and extremely important for contributing.
バグをどういうふうに管理してきたということですね。最初は、そんなに大きなかったので、自分で知らせたんですけども、どんどんそれが手に負えなくなってきてですね、最初テキストでファイルで作ったのがですね、いろんな人で手分けしてやるようになって、最終的にはバグジラを使ってやるようになった。基本的にバグジラというのが、Linux のサブシステムでは、インフォーマルですけれども、使われているということですね。ACPI は、問題が多いんで、それはちょっと違うふうにやってるんですけれども、ですね、あとバグリスターの言い方ですか。Could you talk a little bit about Bugmaster again?
Yeah, sure. The Bugmaster, because, for example, you have a bug database or people submitting bugs, and when end user submits bugs, they typically need somebody to work with them, to just ask for quiet information, work with them, and ask later on, is the bug still current, and so on. And that's a lot of work. You have to do a lot of interaction. And basically a bug master is just somebody who makes sure that bugs were coming in are high quality, so that only the high quality bugs which have information actually go to developers. So it's a kind of a filter. And it also is extremely useful to categorize the bugs, so you can determine this.
But you do the filter function.
It's a filter function, but also a categorizing function. It's basically managing bugs, a bug manager. Yeah.
そうですね、バグマスターという人がいてですね、いろんな、システムにやってくるとバグがたくさん出てくるんですけども、重要なやつとそうじゃないやつとか、いろんなカテゴリーに分けて、きちっとやっていける人がやっぱり大事になってくるんですね。問題点を作り込んで、不便な素敵な問題点とか、そういったところをやってくれる。そういったバグバスターというのが重要になっていて、そこの人たちが重要なバグを開発者に投げていくっていうのが、で、開発者が、それに対して、素早く開発していくことが大事だといったところをお話しします。
Question: How does committee assign bug masters?
Doesn't really assign. Somebody does it, and then they are the bug master, or one of the bug masters.
Okay, so it's a kind of reviewer of.
It's a kind of reviewer for bugs there. And it's not a very popular. There are not many people doing this, so there are not many of them. But in my opinion, it's extremely important because they're making sure the quality stays high.
Yeah. So how many bug masters do you have?
At least in the kernel Bugzilla, so people who are doing lots of subsystems, I think it's only 3 or something.
Who is?
One of them is Rafael Bisocchi, and there's Natalie Ochavich. That's another one. And there are a couple of maintainers who are doing bug, well, people who are doing bug mastering for specific areas, but there are not many of them. Yeah.
コードレビューアーがいないのと同時にバグマスターもあまりいない。ちょっとこれ私の個人的な意見なんですけども、こういう問題点をきちんとこう分けていくっていうのは日本人は得意なんじゃないかなということで、結構日本人がこういったところに関わるいい場所じゃないかなという個人的に思ってます。
Okay, so that Andrew Morton has a lot of bug mastering.
小崎さん
Okay, any further questions?
Okay.
So last pause, finally finished. It's very motivating when your code is widely used. So of course, as I said, when you're going from the novelty phase to the commodity phase, it's a lot more work and you don't code as much anymore because you're becoming a manager. But it's also very motivating when you know that so many people are using the code. So I found this very motivating, but it's also a lot of work. Okay, thank you very much.
質問とかはいかがですかね。何かありますかね。多分おそろいさんが強いしてる勝手に期待して。
Do you have any questions?
Do you enjoy the work as a maintainer, or do you want to go back to code developer sometime?
Well, I went back to code developer. I'm not an x86 maintainer anymore. So yeah, at some point, basically at some point when you did something for a long time, and you think about what the options are. So at some point that's when I want to change. So yeah, and this time, actually, you know, I do a lot of other things. Again, not coding too much, but at least some coding and enjoy coding.
So how many hours do you spend for Linux
Oh,
a day?
I don't keep track. But it's a lot of hours.
100%?
Oh, you mean today?
Yeah.
My work. Luckily, some of the work I'm doing for Intel is also, okay, a lot of it is Linux, I would say 80+%, but also doing some work like on hardware, not directly working on hardware, but just talking to people, so some part of it's And of course, when you're in a big company, you have to spend some time on paperwork.
Yeah.
That's also it. But I cannot put a percentage in it. But at least the majority of my work is Linux.
Do you sometimes visit to customers?
Yeah. So that's actually one of the reasons I went here to Tokyo. That's some customer visits.
Oh, by the way, where do you live?
In Germany.
Germany. Okay. Do you have Linux users group in German?
Yeah, there are multiple ones in many cities. The user groups. Also, I live in a city called Bremen. It's a smaller city, but it has a Linux users group. Yeah.
Is it active?
Yeah, reasonable.
Reasonable.
Yeah. But I think they're larger ones, but it's existing and so on.
Okay.
How do you feel about this?
Sorry?
How do you think about this?
It's a very large users group. So I've seen smaller ones. That's pretty good.
How the Linux is popular in Germany?
Very popular.
Very popular.
Yeah.
I like the popular in the public segment, like city. Local government.
Yeah, there's quite a lot of things going on. That there were, for example, it was very famous that the city of Munich moved over to Linux. So there are definitely big projects and a lot of interest from the government working on this. Yeah. So for example, there was even a government Linux distribution at some point. Like they have this government agency who specializes on IT security, and they put out something like this. So there's a lot going on there.
Do you use usually kernel debuggers or some tools?
Well, at the beginning, when I was still in the simulator phase, you can do lots of interesting things with simulators. For example, simulator, you can turn on a log file and logs everything you're doing. So we did a lot of stuff just going over log files. Today, actually I don't use kernel debuggers too much. I just mostly go through code and review crash dumps and things like this. So occasionally I use them, but not very often.
May I ask?
Yeah.
What kind of tests do you do and you manage
Well, the first test, of course, doesn't even compile. It's actually interesting because there are so many config options in the kernel. Like there are hundreds or probably even thousands now of config options. So it can be challenging to get all the combinations of if-defs to compile. But basically what I did then was I compiled a couple of kernels and then booted it in several systems. Like I had a setup where they were using NFS root, so I could boot them extremely quickly and also move over to different user lands. And what I later on developed, but it was pretty late in the project, is I had also an automatic test system that would automatically boot systems and wait, see if they booted and then lock it and so on. That was called auto boot.
I see.
And of course some tests, LTP I used a lot and some other tests.
Okay.